Hello, everyone. Welcome to the Vision Seminar. Today, it's a pleasure to have Philipp Krähenbühl with us. Philipp is an assistant professor in the Department of Computer Science at the University of Texas, Austin. He received his PhD in 2014 from Stanford University, and after that, he spent 2 years as a postdoc at UC Berkeley. Philipp works on computer vision, machine learning, and computer graphics, and specifically, he's done a lot of great work in scene and video understanding, with applications to object detection, segmentation, action recognition, and tracking, among many others. Philipp, we're very excited to have you here, and welcome to the Vision Seminar.
All right. Thank you very much. So I'm not going to talk about any of the detection and recognition stuff. Well, maybe a little bit of recognition today, but I'm going to talk about sort of driving today. And I'm going to start with sort of a brief history of autonomous navigation. I don't know if many of you knew that the first self-driving car actually dates back to 1926. And what that car did was essentially, there was a radio antenna on top of the car that could control the steering wheel and the acceleration. And then there was another car right behind it, sort of right here, that would control sort of that first car. Now, you might think, okay, well, this is not really autonomous driving. It turns out that's actually some of the earliest demos we've seen out of Tesla. This is more or less how they drove the car for these autonomous driving demos. And so it's somewhat autonomous. It's not really what we want, though. Then in the 60s, 70s, people started to sort of drop at the first concepts of autonomous cars. None of them were ever built. So the vision there was to either follow some sort of wire that was built into the road, or to even have cameras or some sort of sensors to perceive where the road is and follow it. None of them were ever built. The first autonomous car that I know of was Alvin. That was built in the very late 80s, and sort of the project continued throughout the 90s. And sort of the modern version of autonomous vehicles really came along with the DARPA challenge, 2005 to 2007. Actually, it should be 2004 to 2007, I think. And then sort of that translated into some success in industry. Now, I would like to look at sort of the last 3 entries here in a little bit more detail, because it's educational to see where things went and where they could have gone. And we'll start with Alvin. So Alvin was an old military ambulance that was converted into a self-driving vehicle. So in the back of Alvin here, there was it a 5,000 watt generator and sort of a few refrigerator-sized computers. And on top here, there's a camera and a rangefinder that will give you 2 images. And so one sort of is a very pixelated and low resolution color image, and the other one is an image that sort of measures how far away each pixel is. And the output of Alvin is 45 discrete directions you could go and steer. And then they trained Alvin using 5 minutes of real driving data, and it actually learned to drive. It learned to drive at about 1.5 to 2 miles per hour. All right. And they even did this using a deep network before sort of deep networks were really cool, or maybe last time deep networks were really cool, right? And that was pretty much it. So that's sort of how far Alvin got. Now, in the 2004, 2005, and 2007, DARPA had a series of grand challenges where they sort of wanted to see if they can build vehicles that can navigate completely autonomously. And sort of the contrast to Alvin was that these vehicles now all of a sudden had a lot more sensors. All of the vehicles that participated at least one LiDAR sensor, plenty of cameras, some had radars. And instead of learning everything end to end like Alvin did, from pixels directly to controls, they now started to design these very uniform modular pipelines. So each of these teams started to converge on almost the same solution, which is you have some perception. And back then, a lot of the perception was actually reasonably hand designed. There was not a lot of learning in it. And that's where LiDAR comes in. LiDAR is quite good at sort of segmenting out the ground you can drive on from the rest, because you can just look at sort of the ground plane and just subtract it, and then everything else, all the other connected components, might be objects you should avoid. Planning and control were also just hand designed. Planning means you want to find sort of a trajectory that you want to follow, and then control means how do you translate this trajectory to raw actions of the vehicle. If you look at vehicles today, not much actually changed. So if you look at sort of the Waymo, the Argo, or the Neuro vehicle, not a lot changed in them. They have very similar sensors, and the pipelines they work with are still fairly modular. The only thing that changes, at least for computer vision, this is all now learning based. They have gigantic data sets, and they learn a computer vision component sort of from that large amount of labeled data. Planning and control, it's a bit debatable, but I think for most companies this is still mainly hand designed, where they hand design a controller and hand design a planner, and then have sort of some fancier version of a PID controller to translate this into actions. And the reason for this is actually quite simple. The people that did the DARPA Grand Challenge were the ones that then ended up building all of these self-driving vehicles. So Sebastian Thrun was one of the sort of early members of Waymo. The same for all of the CMU team. They joined Waymo. And Kyle Walker, who's an undergrad working on Talos, later founded Cruise. Now, Chris Urmson is now at Aurora. I think Dave Ferguson is at Neuro, and Brian Zaleski is at Argo. And so all of these people sort of knew each other, they knew what they were doing, and so they just started to scale this up into sort of larger industrial prototypes. Now, if we go back into sort of the history of driving, sort of we had sort of these early aspirational things, and then we actually had a solution that many of us would probably think this is the way to go. Like we had a solution that was all learning based. It was just way too early. It came about 10, 20 years, or maybe 20, 30 years before its time, because they couldn't learn all components of it. And then we started going back to sort of engineering solutions that were also sort of hand designed, and we're sort of facing the issue that these hand design solutions might not scale to sort of the domains or the real world as we want. And so what sort of where some of the research is going right now, at least for today's cars, is make vision a lot more robust. That is, maybe not fully rely on LiDAR anymore, and I'll get back to why fully relying on LiDAR is an issue. And then also there's more and more of a push to learn all components of the driving stack from data, and not just learn just the perception part. All right. Now you might think, okay, well, what happened to the team behind Alvin? They seem to have sort of the right idea. They had the right idea just about 20 years too early. Now, this is actually a very funny story. It's Dean Parmelo. When they discontinued Alvin, he went to go and work on driver's assist quite successfully. And I think in about 2005 or so, he completely gave up on driving, and he became a goldfish trainer. So you can still look this up online. Yeah, so apparently, the story behind this is that he and his brother, when they were young, they figured out how to sort of teach their own goldfish some tricks. And he decided, well, I've done enough driving, I'll make this a business. And there's actually a site where you can sort of get his videos on how to train your goldfish to do some fun tricks. Yeah. So I think if he would have been about 20 years later, he would be a very rich man right now. Well, he probably is. Maybe he is a rich man. I don't know how much goldfish training he makes, but yeah. All right. So what are we going to talk about today then? So today we're going to talk about sort of how to make vision more robust, and we're going to look at sort of how can we learn vision right now without LiDAR. I don't think it's the greatest idea to completely ignore LiDAR. I think LiDAR still has value, radar has value too, but just as a problem setup, can we sort of learn 3D perception from the perspective of the ego vehicle from just cameras. And I'll get to why cameras are a good thing in a second. And then in the second part of the talk, I'll talk a little bit, and once we have the perception module, how can we learn planning and hopefully later also control from data directly. So let's dive into the first part. And so learning a perception system that doesn't use the LiDAR sensor here, but instead uses cameras that are mounted all around the vehicle. I think there's one here, there's one here, there's one here, and so on. And so the nice thing about LiDAR perception is, as I mentioned before, that everything sticks out from the ground, and like it's very easy to separate objects from the rest. And we have had some work in the past that did quite well on LiDAR 3D detection. The main issue, though, is if you look at the performance of that work, it starts to degrade very, very quickly as you look at objects that are further and further away. So if you're sort of look at an object that's within 15 meters of the ego vehicle, you get a MAP, which is mean average precision, of about 76. And for those of you who do object detection, 76 is something, if you would publish this on COCO, people probably would stop working on it. This is really, really good. But then if you start to go look at objects that are further away, let's say about 15 to 30 meters, this starts to drop. So now 60 is still very good, and it's roughly the limit of what we can reach in COCO right now if you compare this to 2D detection. But if you look at objects that are further away, 30 to 50 meters, we are now at a pretty terrible performance. So you can think of this as sort of, you can flip a coin, and you might or might not see you might or might not detect the object at the right location. Now, for half of them, you still detect them right, and for the other half, they're just not there anymore. And this is not a problem if you go slowly. So if you drive slowly, if you're somewhere sort of in a city, you never go beyond 20 miles an hour, this is probably fine. You have enough reaction time. If you think of a scenario where you're on a freeway and go about 65 miles per hour, you're almost at 30 meters per second, which means that in order to get to this sort of range where you can see objects here, you have about a 1 second reaction time. And that's pretty rough. Like, you have to have a very good control to be able to deal with a detection that gets you with detections that only become good once you have sort of a 1 second reaction time. And that is, by the way, for vehicles. It gets a lot worse for pedestrians or for smaller objects that might lie on the road. And the main reason for this is just that LiDAR is way too sparse. So here I'm showing you a color image, and then the white dots on top are LiDAR measurements. And so these LiDAR measurements come in sort of different rows. And there's a lot of measurements along one of these rows, but then there is sort of a gap between two different rows here. And so that gap simply just comes from the setup of the sensor. And if you look at sort of how many measurements we have from LiDAR to an average sized color image, it's about 10 to 100 times fewer LiDAR measurements. And if you zoom into this image a little bit, you can see that, for example, you can still see the pedestrian quite well here in a color image, but for LiDAR, you would only see about 2 points or 3 points, and you would have to detect that this was a pedestrian. And so that's why the performance of these LiDAR-based detectors drops off very drastically the further you are away. Now, one thing you might ask, okay, well, why don't we just buy a better LiDAR sensor? So what I've shown you above was captured with a 64-lane LiDAR sensor. It costs about $3,000. If you would want to double the resolution, you would spend about $100,000. That's at least last time I checked. And so this is just, if you now, in order to drive well, you would have to now spend $100,000 on just one sensor. I don't think you will ever be able to sell a car that's self-driving at this cost. Now, on the other hand, if you look at a color camera, if you go on Amazon, you can find a color camera for $25 that has at least 10x the resolution. The issue is just that you don't have a lot of good depth measurements. And so that's where our problem setup comes in. It's like, well, can we still reconstruct depth? Can we still perceive things in 3D from just a bunch of color images? And we assume here that we actually have calibrated cameras. So we have cameras, we know their location relative to one another, and we know their location relative to the vehicle. And now we know how to project one point from the camera out into the scene along a ray. All right. Now these cameras are also slightly overlapping. So you'd see this part of the camera here overlaps with this part over here. You have sort of this part here, overlap here, and then you have sort of an overlap between these here. You have an overlap. So this the bottom row is sort of sorted differently. So you have an overlap over here, and so on and so forth. Now, in practice, you would actually have way more cameras for redundancy. You won't want to still be able to drive if one camera falls out, but at least for the data sets that we have available online, they only give us the non-redundant camera views. And now the question is, can we use this? Can we use this slight overlap and maybe also prior on how scenes look like to still do accurate 3D detection? And so what accurate 3D detection, or 3D, in this case, we use semantic segmentation, is we want to estimate sort of the layout of the scene around us in a map view in 3D, while each of the images just looks into this scene. All right, are there any questions about the setup? No. Yes, there is a question. Okay.
Thanks, we're moving. No, we're
not.
Oh yeah, I just wonder, like, I know, like, for this setup, it's what's available in dataset. But I feel like if we have like stereo cameras, this probably will become a lot easier. And like double $25 is pretty cheap also.
Yeah, exactly. I think that with stereo cameras, it's still a little bit annoying to synchronize them. So I think they're not $25. If you want them synchronized, the stereo cameras are not $25, but there's definitely stereo setups that are cheap. Yeah. I think the issue is that if you want to do well in stereo, at least when you're driving, you need to either sort of synchronize the scan lines of the camera, or have a camera that has the memory on chip and doesn't need to do scan lines along the chip. Anyway, it doesn't make that big of a difference, but yes, I think most companies will probably switch to stereo camera. All right. All right. So our goal here is to get a 3D understanding of the scene from multiple input views, and then project them onto a map. And so we would like to sort of match and align these input views. So we will have, for example, this view up here would sort of cover this part. The view up here would cover sort of this part over here, and so on and so forth. And we'd like to fuse information. So if there is sort of an overlap between views, we would want to have a system that is able to sort of figure out how to do the best possible job at this 3D vision using all the information available. And at the same time, we also need to estimate depth. So for each of these cameras, if there is sort of no overlap in the area where there's no overlap, for now, we need to estimate depth. If you have stereo pairs, we could forego this and we wouldn't have to estimate depth. The stereo pair could give us depth. All right. All right. So option number one is really just to do stereo and to do depth estimates. And this would work quite well if you didn't have an overlap. So if you just did sort of for each view, here you had a stereo pair and did depth, you could figure out how far each part is. You could do the semantic segmentation in either of the stereo pairs or maybe in both of them, and then project that information, that segmentation information into the scene. You would have to deal with sort of what to do once things overlap. but I think you probably could get around this. Now, the issue right now is that in the current data sets, we can only do stereo in the areas where things actually overlap. We don't have the data to do stereo anywhere else. And so we could only do stereo in a very, very narrow area in the data set we have. And then the other issue is that the cameras are not parallel. So stereo actually becomes a lot harder. So you would have to rectify the images and sort of align their relative views to feed it into a regular stereo algorithm. And so that rectification is actually quite brittle if the cameras are not nicely calibrated in parallel. Right? So we didn't choose this. Now, try number 2 would be to just use monocular depth. And so this is what lift, splat, shoot, or Fiery use. These are sort of 2 competing methods. What they do is they get a monodepth estimate, and then just project all the information from the image into sort of the scene here. If there is an overlap, I think they just average the overlapping regions. But that relies on having a very good monocular depth estimate, which is fine. You can do well for sort of the area that's close to you. It might start to break a little bit for areas that are further away. The other issue here is that things can actually sort of get quite slow when you do this reprojection, and we'll see this in the results later. And so issue number 1, monodepth is sort of inaccurate, especially further away. And in the area here, the monodepth estimate is sort of inconsistent, and it completely ignores the fact that you actually have the same thing. You see the same thing from 2 views, which will give you the capability to estimate that. All right, now let's take a little bit of let's go off on a tangent a little bit. And let's assume I gave you, for every point on the map here, I gave you height above ground. So I would tell you how far above ground a certain point on the map is. So I'll tell you a point on the vehicle is maybe half a meter above ground. The point on the road is completely flat. It's at sort of at 0. And maybe here on the side, there's a little bit of elevation. Now, if I gave you this from the map itself, you could just use elementary geometry to project all the points from the map into each of the views here, right? And you would essentially get a correspondence from a point in the map to a point in an image, right? Now, the issue is that you don't know the height above ground. But what you can do is you can start to sort of learn this height above ground, which we'll do in our method. All right. And so what we're doing here is we're phrasing all of this as a gigantic transformer. And the height above ground estimate is going to be the positional embedding. It's going to be one part of the positional embedding of the transformer. And so what we're doing is we're sort of take a transformer, and for each point in the map, we're finding an embedding. Let's call it Q for a query. And so we're learning an embedding. And then for each point in the image, we're going to use the calibrated position and direction of each of the rays in the camera as a key. So we have a key that says, hey, I'm pixel 50 in camera 10, and my camera center is at location A, and I'm looking along a certain direction B, right? And now what I can do is I can take this completely abstract sort of concept of a query or an embedding here. I can find a second embedding that has the information about where a camera is and which direction each pixel looks at. I'll embed this too, and then I can just learn the geometric reprojection from each of the images to this common map as just one transformer operation. And so I don't need to worry about how geometry works. All I do is I'm going to give the network all the information it needs to figure out how geometry works. All right. And so maybe to sort of illustrate this, we'll have a camera here. And what we're doing here is for the keys, we have the camera center plus the direction each pixel points to. And that will go into an embedding. Oh, sorry. All right. Sorry, I have to draw this again. Camera. Direction. So we have center and direction. That will go into an embedding for the key. And then we're going to learn and build up over multiple iterations an embedding for each of the locations in here, which is the query. And so what we can do is we can now just use cross-attention between the keys that have all the geometric information about the camera and some abstract feature that we learned that hopefully contains sort of distance above ground from the map's perspective. We use cross-attention to get all the information, sort of that all the corresponding information from the images into the map view. And then we'll have a little MLP to update the queries here, and then we'll repeat this thing over and over again. Right? So this way, we don't ever have to think how geometry works. We just give it enough information for the network to figure out how geometry works.
Question.
Yes, there's a question, yes.
Hey, I have two questions actually. So first,
Yes.
why, like, what's the addition that transformer brings compared to like MLP to solve if it's just a geometry problem? And second, is it like unsupervised? How do you supervise the correspondence in the?
Yeah. So the second question is easier to answer. The correspondence is unsupervised. It's just learned as the positional embedding of a transformer. The transformer is supervised to produce the right semantic segmentation. So sort of the output of the network here, this here is supervised.
Gotcha.
But we don't ever tell sort of the cross attention here what sort of keys and queries should be and how they should match. We just have enough training data and hope that the network will eventually figure this out.
Gotcha.
And it somewhat does. Some results later that show that it does to a certain extent. Now, why do we need the transformer? Now, the reason why we need the transformer is because we would like to learn this map encoding, this positional encoding of the map. And I don't think there is a very elegant other way to do this. You could learn it, maybe if you had the exact geometric relationship, you could just do lookups, and you could learn explicit height above ground. But I think just a free-form embedding is easier to learn.
I have a question. Why do we expect that it will learn height above ground and not something else spurious to the image, I guess?
Yeah. The height of above ground is just, I think it was just sort of, you could do it if you knew height above ground. In practice, it actually doesn't learn height above ground. It learns appearance. In a lot of ways, it learns to attach sort of not just geometry, but also appearance to each of the points in the map. And that's how it starts to pull in similar things.
In that case, would it be helpful to have some sort of bottleneck to like inject some sort of constraint into your intermediate embeddings?
Yeah, so maybe I'll walk this back one step. So in the very first iteration, it does need to learn geometry. It learns a prior on what in the average scene, what matches to what. And so it learns sort of geometric prior, what is sort of the average sort of correspondence between a point in the map and a point in each of the images. And then once it sort of continues, once we do cross attention again, then it starts to learn appearance. Yeah. Yeah. Good. Other questions? No. Okay. Yeah, and in general, this works quite well. So we compared to quite a few state-of-the-art methods. I think one of the most competitive one is Fiery here. And we're able to sort of get to the same performance as Fiery, but we're about, was it 5 times faster here than Fiery? And Fiery is sort of the geometric equivalent to what we do. And just phrasing things as a transformer without thinking about it turns out just to be slightly more efficient. It also works quite well like this here was a vehicle on nuScenes. We also do drivable area on nuScenes, and there we get sort of a healthy boost over prior methods. Now, Fiery didn't do this, so we don't have a good comparison. And I can also show you sort of a result video. And what we do here is we use the odometry of the vehicle and just integrate the map that we produce over time. And you can see sort of, this is just for road segmentation. You can see how the vehicle builds up road segmentation as we continue along the video. Here's another example. And I hope you can see it. Yeah, and so this is a very simple temporal extension where we just average all predictions. If you have multiple predictions that sort of come one after the other, we just average them together. Here's a third one. And so to visualize a little bit in what the network learns, we also started to visualize attention maps. So we looked at one specific vehicle or one specific location in the map and looked at where does attention focus on. And you can see most of the focus is on the vehicle here. There's a little bit of focus down here. For the next example here, this is the vehicle that's ahead of us. And again, most of the attention is right on the vehicle ahead of us. And so it learned the geometric correspondence somewhat without us ever telling it that it needs to. Here we switch to a different vehicle. Yeah. Are there any questions before we move on? No. All right, good. So this was the first part. In the second part, I'll talk a little bit on how we can use learning to not just learn the sort of the perception part of the pipeline, but how we can also learn motion planning, which is sort of what follows next directly from data. Now, the controller in the last part is still not learned from data, it's still hand-tuned, but we're working on making this learnable as well. And so for the second part of the talk, we'll go into Carla. So this is a 3D driving simulator. Somewhat photorealistic. It's not as photorealistic as sort of the newest, coolest Nerf demos, but it looks okay-ish for research experiments. And the driving stack that most people use in Carla is sort of a very simplified version of real driving stack. So you have some sort of perception module followed by some sort of module that produces an action. And for perception, really, the first part scaled up is probably gonna be fine, and we're gonna be on a good track if we just make this larger. Now, for the action part, or for the part that produces commands, there we're actually facing quite some difficulties, which is the number of weird behaviors that you can see on the road is actually quite a bit larger than the number of weird objects that you can see. And a lot of these behaviors are very safety critical. if your perception system doesn't see a pedestrian that's 100 meters out, it's probably fine. If you don't plan well for the next 2-3 seconds, you're going to crash the car into a tree. And so the way perception is often formulated is as learning a policy where you go from observations. In our case, this is the output of the perception system. And now, sorry, the way that driving is formulated or acting is formulated is you go from observations, which is the output of the perception system, to actions, right? Now, oftentimes we split this into 2 parts. One part says, okay, we go from observations to sort of a trajectory where we would like to drive, and then we translate this trajectory into low-level actions. By far the most fundamental way to learn planning and control is to just learn it through imitation learning, where the policy goes from observations to actions or from observations to waypoints. You have some recorded data set of observations paired with actions or trajectories, which is shown down here. And then you just apply supervised learning on it and just say, hey, if you see this observation, you execute this action, or you plan this trajectory. And this is actually how Alvin learned their end-to-end system. And this is also sort of how some of the more successful approaches on Carla learn their control or their planning. Now, on Carla, vanilla imitation learning doesn't work that well. You either have to inject noise while you drive, or you have to do sort of a 2-stage learning approach where you first learn to plan using ground truth vision inputs, and then you have to learn perception and planning together. Now, the reason why vanilla imitation learning doesn't work very well in Carla is that if during training you've always only seen perfect driving that's in the center of the road, as soon as you start to sort of go a little bit off the road, you're in a domain that you've never seen during training, and things can go arbitrarily bad. And so the general sort of consensus here is that you either need to do some data augmentation, which is when you drive, you inject random noise into it. So you sort of swerve off the road a little bit, and then you learn how to recover. Or you can do this 2-stage learning approach where you first have a planner that operates on ground truth vision, and that planner generalizes quite well. Even if you don't train it on sort of going off the road, it will learn to still stay on the road. And then you can just do imitation learning or sort of distillation to get an image-based agent out of this that is also robust.
Question?
All right. Yes, question.
How is like uncertainty in imitation learning handled usually? Because if you are training some sort of regression model, and it sort of regress to some like very suboptimal solutions. Right?
Yes, this is a great question, and the short answer is it is not handled.
I see.
Yeah. So and it actually gets worse than this. So in imitation learning, also, you don't know. So you know that the action that you've seen was sort of good because the person that executed it didn't crash, or most of the time they didn't crash, right?
Mm.
But you don't know what other actions would have been also good and led to sort of a successful outcome, right? And so that goes sort of hand in hand with uncertainty. Like you would actually like to know for every action what is the right way to. So what, like, for every action, we'd like to know if it's possible to still drive well if you execute this action, or if it's not possible. Mm-hmm. We have some work from, was it ICCV last year, where we looked at how we can formulate reinforcement learning inside of some of these agents. But there we have to make an assumption that sort of the world does not react to the agent. And so then you can formulate reinforcement learning, and then you can get a supervisory signal for all actions. Here, I'll keep it simple, and we'll just stick with imitation. Yeah. Yeah. So
one more question.
Yes.
So for imitation learning, practically, where does the data come from? Is it like like human generated data?
Yeah. So in the earliest Carla demos, it was human generated. I think somebody sat down for 25 hours and drove Carla for 25 hours. By now, this is generated using an autopilot. Carla has decent autopilots now, and so that's what people use to roll out these trajectories. The autopilot is not perfect, and sort of an ugly hack to deal with this is that whenever the autopilot did mess up, you just don't use this to train. Yeah. And the autopilot is getting better. Yeah. Now the issue is really, like, even if you do this in the real world, near accidents are quite rare. Most of the time you will just see sort of boring, safe driving. And I can show you this in sort of a video. If you look at, where's this? This is a video. If you just look at sort of the data sets that people collected, you could train on these, but most of the time the ego vehicle doesn't do anything interesting. Like, it just stands around, and there's a driver in this like $100,000 or $200,000 vehicle, and they really, really don't want to crash the vehicle. They don't want to do anything that might endanger the vehicle. They don't want to show you the data that you would actually need to learn from if you get into sort of close call situations, right? Mm-hmm. Now, if you would want to go and look at sort of this data, you could go onto, there's this Reddit subreddit, it's called Idiots on Cars, and there's plenty of examples of people sort of driving dangerously in these scenarios, right? And so you could get plenty of fun examples of people not driving well. It's not really in the format you want, and it's not really something you can train on. And so what do we do? Well, so our idea here is that while the ego vehicle itself doesn't get into trouble that often if you have a good driver, you might still observe other vehicles that sort of get into more dangerous situations or more interesting and interactive situations. And so if you start to observe other vehicles driving, there's actually a very interesting effect here. So if you would learn from other vehicles what they do in other situations, you actually get a much richer training signal for denser traffic scenes. So the more interesting traffic scenes are scenes where you have lots of vehicles interact with one another. And from those, you will now get a training signal from each other vehicle that you could observe, if you could learn from them. Right? The main issue is that these other vehicles are not going to have the sensors that you want. They're not autonomous, and you don't know their actions and you don't know their goals. Right? And so in the next few slides, I'll show you a pipeline that we developed that sort of is able to learn a driving policy that sort of solves both of these issues, that sort of goes around these two issues, which then allows you to learn to drive or learn to sort of plan from all other vehicles that you observe. And is there a question? Okay, good. And so this is really a three-step process. And the first step, we just learn a perception system. And we're actually going to freeze this. So we learn a perception system that does sort of the mapping similar to what we have seen before. And in this case, it also does 3D detection, and we do use LiDAR as an input. All right. We also use multiple different color cameras as an input to make sure that we can deal with the resolution issues of LiDAR. Then in the second step, we're completely ignoring perception, and we're using ground truth computer vision labels. So if you go back to the first step, this is sort of the ground truth that we use to supervise this. And we now use this as an input to a motion planner. So the motion planner gets to see the ground truth label of the scene. And its goal is to predict future trajectories of the ego vehicle or all other vehicles. Now for the ego vehicle, we know where the ego vehicle wants to go. We can record this during training. We can say, if you want to drive from Berkeley to Stanford, we can just say, hey, the next location is going to be Stanford. That's our goal. And we can condition on this. And so if you want to go from Berkeley to Stanford, you want to turn left at whatever intersection, we now sort of disambiguate sort of different possible road, different possible decisions on the road, and the prediction problem becomes almost unimodal. And so for the ego vehicle here, we feed in the ground truth sort of labels from the perception system, and we predict one single future trajectory that says, if your goal is to sort of turn left, this is the trajectory that you should follow. Now, for all other vehicles, we don't know what their goal is. We don't actually know if they want to turn left, they want to turn right, or what they want to do. And so what we do is, we try two things. Number one is we can enumerate all and then predict which one to use using the future of the future motion plan, or we can just predict all and then use sort of the one that fits best. Right? And so this way we can learn from just the future observations of the other vehicles, we can learn to sort of plan for them. Without knowing what they actually wanted to do, we can just look at the future and infer what they wanted to do, and then learn the same motion planner. Now, the most important thing here is that the motion planner for ego and for the other vehicles is the same network, right? It gets to see the same inputs, just centered at a different view, and it gets to produce the same trajectories. For ego, we only pick one, the one that corresponds to sort of the goal it wants, and for others, we predicted for all goals. And yes, there's the question, Ishan.
Yeah, thank you, Professor. So when you say that you're conditioning on the goal here, there are like, it's not like a future location-based goal, right? It's like a set of high-level goals or something like that. Like
yeah, so
move right, move left, go straight through, things like that.
Yeah. So right now, what I refer to is move. Yeah, I think it's move left, or like switch lane left, switch lane right, turn left, turn right, go straight, follow the lane, this sort of goal. Carla does provide you with a point in the future that you should reach. We use this, but it's too detailed on how we actually use this. We just use this to refine the motion trajectory a little bit.
Right. The argmax approach would not work with that second kind of goal, right? Like you would not have, like,
yes,
when you say which is the best fitting one, right? Because that would just be too many goals, I think.
Yes, not unless you could enumerate them somehow. I mean, you could, in theory, you could look at where they went after, right? And then use that, or sort of a noisy version of that as the target goal. But yes, it's a lot more complicated.
Got it. Thank you.
Yeah. That was a very good question. Thank you. All right. So that's step number 2. Now, step number 3 is we just put 1 and 2 together, more or less. And so what we do is we freeze our vision backbone, just plug it in here, and then we learn a new motion planning backbone that uses the features of the vision network. Now, instead of using ground truth vision, we now use the features, so the layer before the last layer in the 3D backbone. And we use the ground truth vision labels with our motion planning expert here to now produce trajectories to supervise our new motion plan. So since we still have sort of paired images and labels, we can now use the labels to infer trajectories using the motion planner that we got from step 2. And now we just use these trajectories to supervise a new motion planner that uses our perception system. Right? This is, again, just supervised learning. All right, and so the result is a network that is able, at test time, is able to take as an input LiDAR, RGB from the ego vehicle's perspective. We have a vision network that produces some intermediate representation. And from there, we have a motion planner that is conditioned on a high-level command and predicts a trajectory. Now, that motion planner is now learned from a supervised signal that observes all other vehicles, not just the ego vehicle. So it gets a much denser or richer supervision. Now the controller here is just still just a PID controller, and what it does, it just translates XY locations along the trajectory into steering and acceleration. Right. Now, why does this work? Why is this even a good idea? Well, remember we had these two issues. Issue number one is there's no sensor readings from other vehicles, so we couldn't directly train on them. And issue number two is we don't know the goals and actions. Now, the sensor readings, we sort of sidestep by first learning a perception system. And most importantly, we learn the perception system such that we output the same labels for all the cars in the scene. So in this perception system, we also predict a detection for the ego vehicle, and we also predict sort of the semantic segmentation that would be underneath the ego vehicle. And so it turns out if you do this, so if you just go one layer back in the network, the representation is still similar enough between the ego vehicle and other vehicles in the scene, so that you can just crop from another perspective. And so one way to think about this is more or less like what faster RCNN does with sort of the ROI align. Okay. Now, why don't we need to know the actions and the goals? Well, the reason why don't need to know the actions is because we just predict the future locations or the future trajectory of the other vehicles and of ego. And the reason why I don't need to know the goals is because we have a loss that just says it doesn't like that infers the goal of other vehicles. Okay. Questions? All right, good. We can even do a little bit more at test time, and so this helps a little bit, which is at test time right now, the vanilla version, which is predict the ego vehicle trajectory, which we will then execute using a controller. Now, we can also predict trajectories for all other vehicles, and we can have a simple heuristic that says if the trajectory that we predict for other vehicles sort of overlaps with the ego vehicle's trajectory, what we'll do is we'll just slam on the brakes. And so this is sort of what this here does. I think this here is the brake prediction. So we have a very simple heuristic that says if two trajectories overlap, we'll just slam on the brake, we'll produce zero throttle and full brake. And so this is sort of overriding sort of things in emergency situation. And so this way, the fun effect is that we rarely cause traffic accidents. Well, we're rarely at fault for traffic accidents, but if we do this, make this a little bit too aggressive, the other vehicles, the other scripted vehicles in Carla will run into us. But overall, it helps quite a bit. And so this is the agent driving here. What you can see up on the top right is sort of our predictions and what we think where the other vehicles are going. And then on the bottom is the predicted HD map. This is just used, we just use this for supervision. This is actually not used, the predicted HD map is not used in planning at all. And overall, even in Carla, you can see a very similar trend to sort of the larger 3D detection data sets. That is, vehicles that are close are detected well, and vehicles that are further away are not detected all that well. Now, in terms of results, this approach won the Carla challenge last year, and it, at time of publication, was quite a bit better than the prior state of the art. I think we completed 94% of all the routes, and if we consider traffic incidents, we had a driving score, which is sort of traffic incidents times the route completion of 62, which was sort of 1.5 of what the previous best method had. Yes, Ishan, there's another questions.
Yeah, so I just had a question regarding the motion planning again, if that's okay.
Yeah.
Thank you. So my question is sort of regarding the distillation stuff that you mentioned. So is the distillation done to sort of match the ground truth perception domain with whatever domain is the output space-fair perception module?
Yes.
Okay.
And so actually, so if we talk about, we can look at it here, right? The issue here is that the input here is actually the second to last layer of the perception model. It's not the outputs of the perception model. It's not detection and segmentation. It's sort of the layer right before that. And that is different from ground truth vision inputs here. And so that's why we do the final distillation.
I see. So what are the ground truth ROI features? Is it just, do you use some pre-trained network for that?
We just use the ground truth. We literally just use the ground truth. We use the ground truth HD map and crop it out around the
I
vehicle.
see. So there's no ROIs. Oh, I get it. Yeah. There's
No, I mean, it's similar to ROI. It's just simpler. Just crop, rotated crop. Yeah.
Got it. Yeah. Thank you.
And we do this because there's absolute no domain shift, right, between the ground truth of the ego vehicle and the ground truth of other vehicles. And so this motion planning expert gets sort of to learn a representation that is the same for other vehicles and our vehicle. And so that's how we can transfer the information from other vehicle to our vehicle.
Right, that makes sense. Thank you.
Well, another question is that for the current planning network, what exactly is, well, I guess, is the input just a current state, or it also includes some sort of history?
Right now, it's not. It doesn't include history. Yeah, there's a sort of a simple reason for why, which is if you start to include history in imitation learning, things go bad. Which is if you look at trajectories, a very good guess for what the next action is just inferring what you previously did. And so if you have too much context or too much history, what the network will learn to do is it will learn to infer what it just did. It will learn to infer its previous action from the inputs that you give it, and it will just repeat that previous action. So it's sometimes called causal confusion. And for most of our models, we deal with this by not giving it more than one frame. There is more elegant ways to deal with causal confusion, but for Carl, at least, just doing the dumb thing and giving it one frame is often sufficient.
This is quite interesting, and it's quite different from what we observe on the robotic manipulation domain. So what we observe is that if we only give it one frame, the future action becomes highly multimodal. And giving the history of the previous action states clears up this quite a bit and make it unimodal and makes it suitable for regression for type prediction.
Yeah.
I guess
so
it's domain specific.
So we do give it like some information about them. We give it the velocity it's currently going on, and so that, like at least in the short horizon, that giving it the velocity already makes it more or less unimodal. Yeah, I really wish we didn't have to deal with this, but yeah, just it's the way it is. All right, I think I'm actually almost at the end here. So if there's any more questions, I'm happy to have a sort of a more open discussion, and I don't want to keep you guys waiting beyond the hour. So.
I see. There's a high level question of, so before I joined PG, I was engineer at Europe, and then part of the reason that I decided to work on manipulation is that I have a feeling that I know a bunch of friends in the industry, and they have so much more resources and data, and I know how costly it is to collect all the data and even just maintaining these data. And so what do you think, what's your perspective on what's the academia's role on this very well-funded industry, and what's the unique contribution that academia can provide?
Yeah, I mean, I think there's maybe two. Academia clearly has a disadvantage in the sense, yes, we don't have the data, and if Waymo doesn't want to share the camera that's backward facing, or they don't want to share sort of nicely overlapping stereo pairs, they don't need to, right? If Waymo doesn't want you to learn to drive on their data set, they can put it in their license agreement, and you cannot learn a policy on it, right? So that's clearly a disadvantage, and I don't think academia should work on making data sets in that space, or should sort of try to compete with them on this. I think the role of academia really is to explore fun ideas, and ideas that people at Waymo probably couldn't, or people at Neuro couldn't, because they actually need to build a product, right? And so I think that's sort of the role I see, at least, of academia. There's still plenty of interesting research to be done, and I don't think we're sort of close to having autonomy solved. And the role of academia is just to do the research. It only works if industry is willing to share data, but for now they are. The other big issue is compute, but most of our models are not that big, so it's still doable.
All right, does anyone have any other questions? Otherwise, we'll move to one-on-one this week.
Thanks so much, Phil.
Yeah, thank you.
Thank you.